Welcome to another video on force method versus method of Stroops. In this video we will analyze an indeterminate truss. This problem is taken from another video, Analyze Pin Jointed Plane Frame by Force Method. You can search for this and it will give you the solution using the force method. In this video we will analyze it using the method of Stroops. You can compare both methods and make comments on which one you find easier to understand and or easier to compute. So we have 4 joints here, A, B, C, D. We have 6 members, no joint at the intersection here. It's basically 3 by 3 meters square. You have supports at A and B. At A it's hinged, only rotation possible, no lateral or vertical displacements. At B it's on rollers, so it can move horizontally but not vertically. It is externally determinate because you have the hinge here and the rollers here. Internally, however, it is indeterminate. You have 1 degree of indeterminacy. For the degree of indeterminacy, you can see the video that I just mentioned. And all members have equal areas of cross section. We will analyze this truss using the method of Stroops, which I developed in my video, Trusses, Electrical Circuits, and Kirchhoff's Laws. And I've used this method of Stroops in other videos to analyze indeterminate trusses. So you can have a look at this video. You don't have to stop now and look at this video. You can view it afterwards. My name, by the way, is Charles DeMattis. I'm a retired lecturer from the University of the West Indies, St. Augustine campus, Trinidad. The university provides me with workspace and other support for making these videos. The first step, as usual, is the transmission of external forces to the supports. So you have these loads here of 30 kilonewtons. This was in the first slide. And 40 kilonewtons horizontally at D. Now you can think of the vertical 30 kilonewtons going straight through this member AC. So this member will have a compressive force of 30 kilonewtons. We denote the compressive forces by a negative number. Now for the 40 horizontal, I will just use these 2 members to transmit the forces to the supports. Because this member will have no horizontal component, the 40 horizontal must be supplied, the horizontal force must be supplied by this member AD. So there will be a tensile force in this member of 40 times root 2 kilonewtons. Now for the vertical equilibrium, this 40 root 2 has to be balanced by a compressive force in BD of negative 40 kilonewtons. You can verify this using elementary statics. Okay, I'm not going into the details, but these member forces will transmit the external forces to the supports. You have 0 force in the other 2 members. Now we will write down the Stroop forces. So we have one single Stroop in this structure A, B, C, D. Again, for an explanation of Stroops, you can look at my video on trusses, electrical circuits, and Kirchhoff's laws, or you can look at previous examples of this method of Stroops that I've made videos on. So basically you have a balanced set of forces, in other words a set of forces in equilibrium in this Stroop. A Stroop is a minimal indeterminate structure. So what we have here is F on the outside edges, outside members, and compressor, and minus F root 2 on the diagonals. I shouldn't say compressive here. I have not put in any arrows to indicate direction of forces. That's because the F could either be positive or negative. A positive force indicates tension, negative value indicates compression. So the F can be negative here also in all of these. Then the compressive force will switch to tensile and vice versa. So these are the Stroop forces. It's a square, so on all outside sides you have F, the same value F. And then we superpose the last two slides, the transmitted forces to the supports and the Stroop forces. So you have F and F at the top and bottom, F minus 30 on this side, F minus 40, minus F root 2 on this diagonal, and 40 root 2 minus F root 2 on this diagonal. These are the superposed forces. Next we go to the compatibility equation. This is a standard rectangular type of Stroop, and we've obtained the compatibility equations which were stated in my video Trusses, Electrical Circuits, and Kirchhoff's Laws. And the form of the compatibility equation is this: the sum of these terms on the perimeter equal to the sum of these terms on the diagonals. For each member you have this term, the square of the length times the force over the area. Strictly speaking, you should have AE in the denominator, but we are assuming AE is the same for all members. So this is the form of the compatibility equation. If AE, I'm writing just A here, but really I should be saying AE. If AE is the same for each member, then you can factor out all of these terms. The A's will be the same throughout. You can factor them out and cancel. And the compatibility equation reduces to this: L squared F equal to summation of L squared F on the perimeter on this side, on the diagonals on the other side. So the coefficients are the squares of the relative member lengths. You don't have to use the actual member lengths. As long as you work with the relative lengths, that's fine. So I'm putting the coefficients here on a diagram. It's a square, so you can think of the sides as being 1 unit each, and on the diagonals the square of root 2 will be 2, so you have 2 as the coefficient on the diagonals. So here I'm putting the previous two diagrams together. These are the coefficients and these are the superposed forces. The compatibility equation is this, which we obtain by multiplying the coefficient times the corresponding force. First you add on the perimeter, you get 1 times F, 1 times F, and then 1 times F minus 30 and 1 times F minus 40. That gives you the left hand side here. On the diagonals it will be 2 times minus F root 2 and 2 times 40 root 2 minus F root 2. Here I've just transcribed from the previous slide. I've just copied and pasted this equation. We can put all the f's on one side. We get 4f plus 4f root 2. Notice we have f, 4 f's here. Carry the f's across, you get this. On the right hand side you'll get 70, that's 30 and 40, and then plus 80 root 2, which gives you 1 plus root 2f equal to 35 over 2 plus 20 root 2. Okay, yes, we are dividing through by 4 also here. Yeah, when we divide through by 4 we get this. And then you can multiply by the conjugate surd here and simplify. F will be 5 over 2 into 9 minus root 2. So once you know F, you can plug in into the diagram with the combined forces and you get the following forces. And here we have the solution. These are the values we obtain. The negative values indicate compression. The positive values indicate tension. Notice that you had a vertical load at C of 30 kilonewtons. Here the compression in this member is only 11 kilonewtons. And you can see that the diagonals take up a lot of the load. A lot of the external load is transmitted through the diagonals. This is another compressive member here, BD, partly due to the horizontal external force at D. Anyway, the solution we obtained by the method of Stroops is exactly the same as obtained with the force method. You can check the video using the force method. It gives exactly these values. So what you can take away here is that the method of Stroops gives the same results as the force method. So it's up to you to decide which one is easier to understand and which one is easier to compute with. So I'm leaving you to make that decision, but you know, I am biased already because I have developed this method called the method of Stroops, and I want to show that it is useful. Now, in other videos that I've done, I've given some extra analysis showing how you can actually use the method of Stroops, and particularly the compatibility equations, to actually help in the design of the structures. In other words, if you want to modify the structure in some way. Initially, in this example, we had all the areas of cross-section being equal. But suppose you wanted to use members of different sizes. In this case, let's consider this this changing of areas, of cross-sectional areas. Suppose the top member, you had a cross-sectional area A1, and in these three side members you had cross-sectional area A2, and on the diagonals you had cross-sectional area A3. You might want this. You might want the top member here to be a different cross-sectional area to the bottom. Why is that? If you look at actual bridge structures, for example, truss bridges, you will see that they have an extra heavy plate at the top, which is lacking at the bottom. And that is because the top members carry compressive forces while the bottom members carry tensile forces. And you need to prevent buckling in those top members. So sometimes you put an extra thick plate at the top there to resist those compressive forces. So let's suppose we have this arrangement of cross-sectional areas. And then the coefficients of the compatibility equation would be these. You no longer have equal areas, so the coefficients will be the square of the lengths divided by the corresponding areas. Okay, so it's on the diagonals, of course, it's 2, that's root 2 squared, divided by the areas A3 in both cases. And you have these coefficients for the sides. So here again I put these two diagrams alongside each other, the coefficients and the superposed forces. Again, to get the compatibility equation, you multiply the coefficient by the corresponding force. You add along the four sides and equate that to the sum on the diagonals. So this is what you get: f over a1 plus f over a2 plus this over a2, this over a2, etc., equal to these diagonal forces over a3. That simplifies to f over a1 plus 3f minus 70 over a2 equal to this over a3. Now suppose we wanted f equal to 20. In the previous analysis we got f to be around 18, but let's just round it off to 20. Suppose so we try to change the areas in such a way that the forces remain approximately the same. So let's just use f equal to 20 just as a wrong number. Well, another reason for choosing 20, of course, is that when you put in 20 into this bracket here, you get 0. So that simplifies things also. So let's put f equal to 20. You get f, which is 20 over a1, and then minus 10 over a2 equal to 0. And that gives you a1 over a2 equal to 2. So here the a1, which is the cross-sectional area of the top member, is twice the cross-sectional area of the other side members. So this is what we want to get. We want a heavier cross-sectional area at the top, and it occurs when f with the forces approximately the same as we had before, with f equal to 20. Notice here that the a3 disappears from this equation. So it doesn't matter what a3 is. You can verify. It doesn't matter if a3 is. As long as you put a1 equal to twice a2 and you solve this, you will get f equal to 20. So in this video, I hope that I have convinced you of a few things. First, that the method of Stroops gives the same result as the force method. That shows essentially it is correct. Second, the method of Stroops is simple to understand and compute with. And third, the method of Stroops has valuable extras. But in particular, the compatibility equations can be used to help in the design, in modifying the areas of cross-section so that you get more or less the same forces as before, but possibly better arrangement of the cross-sectional areas. And once again, my name is Charles DeMatos, retired lecturer from the University of the West Indies, St. Augustine, Trinidad campus. And the university supplies me with a workspace and other support in creating these videos. You can leave comments in the comments section. Let me know what types of problems you are interested in, and whether you find the method of Stroops to be understandable, whether you find it easy to compute with. So I would appreciate any feedback, and I hope you'll continue viewing my videos. Thank you very much.